On this video, we are talking about the structure of GPS signal. First of all, let's look at what is GPS. To understand what is GPS is, basically let's have a comparison between GPS with trilateration course. It's easier to understand these concepts in that way. So GPS can be compared to trilateration, of course, and also uh, the, these both techniques rely on measurement of distances to fix positions. One of the differences between them is, however, the distances are basically called as ranges in GPS. These ranges are not measured to control points on uh, the Earth's surface, but instead of that, they are measured to satellites orbiting an inner circular orbits around the Earth, normally at a nominal altitude of 20,000 kilometers. So when it comes to GPS, it is a passive system. It means satellites transmit signals and also user simply receives them. Such a system is called a passive system. So GPS is passive in the sense that only the satellite transmits signals and the user simply receive them. As a result, there is no limit to the number of GPS receivers. That's one of the advantages of GPS. That may not simultaneously monitor GPS signals. So there are millions of television sets may be turned on to some channel without disrupting the broadcast, and of course millions of GPS receivers may monitor satellite signal without danger of overburdening the system. This is the distinct advantage, but as a result, GPS signals must carry a great deal of information. So GPS receiver must be able to gather all data or information it needs to determine its own position from signals as it collects from the satellite. And here we focus about the requirements of GPS signals. One is method or code, if I may say, to identify each satellite. When it comes to codes in GPS, these codes are basically zeros and ones. In other words, I can say these codes are binary, which are the language of computers. So we are dealing with machinery language here. There are three basic legacy codes in GPS, which have been around from the beginning of the concept. One is precise code, which you may know as P code, and also CA code, which you also known as course acquisition code, and also the navigation code. So there are also new codes now being broadcast by some of GPS satellites. Among these new codes, one is M code and also L2C code, and also there is L1C code. These are some of the new codes which have been introduced later. So these new codes have not yet reached the full operational capability as the previously mentioned code. So, and also all these codes contain, when it comes to the code requirement, all these codes contain information that GPS receivers need to function. They should they must travel from GPS satellites to receivers to deliver them. So carrier waves provide the codes that need to make that journey from satellite to receiver. In order to transport information, a carrier wave has to have at least one characteristic that can be changed into modulated. The characteristic can be carrier wave's phase or amplitude or its frequency. If I give you an example, I can give you an example. Suppose the information, music, or a speech received from a AM radio station, which is encoded to carrier wave by a amplitude modulation. AM means that, and the information on the signal from FM radio station is there because of its frequency modulation. So GPS carriers use phase modulation to do the job. It means looking at some characteristic of wave is as it's a good job towards understanding how it works. So next requirement is location of the satellite or some information on how to determine it. So when it comes to location of the satellite, it's another important requirement of GPS signals. So it is actually time sensitive information. uh, Basically time sensitive informations including subframe 2 and 3 of a navigation message. We explain navigation message in another video. So they contain information about the position of satellite with respect to time. This is called also satellite ephemeris. So that each satellite broadcast to receivers provides information about its position relative to the Earth, and more particularly, it provides information about the positions of the satellite's antenna phase center. So this is given in by using a few parameters, right ascension system of coordinates, uh, which deals with six other orbital elements. One is size of the orbit, uh, that is its semi-major axis, and also its shape, which means eccentricity, and also orientation of the orbital plane in space is defined by other things. So especially right ascension of its ascending nodes and inclination of its plane. So these parameters, along with the argument of perigee, the description of the position of satellite can be given, which is also known as the true anomaly. So all the information will be provided in user's computer therefore. So broadcast ephemeris, however, is far from a bit perfect. It's an imperfect concept. So it is expressed in parameters named by famous astronomer Johannes Kepler. So they appear in Keplerian concepts, but in this case, orbits of the GPS satellites deviate from nice smooth elliptical paths because they are unavoidably influenced by the gravitational and other forces. So the actual path is through space are found in the result of least curve fitting analysis and those procedures. The accuracies of both the broadcast clock correction and broadcast fMRI deteriorate with time. Uh, as a result of that, one of most important parts of portion of navigation message is called IODE or issue of data ephemeris. So that is another requirement of GPS signal, location of the satellite. And also another one is third requirement is the information regarding amount of time elapsed since the signal left the satellite. So when it comes to time, uh, we have to return back to codes and how they are modulated to carry away that movement to help uh, which may help in understanding code generation, of course. So it is useful to cover an aspect of foundation so that the process of time. Actually, it is fundamental to GPS. When come, I have to mention again about the subframes when it will be explained in another video. So both subframe 1 and 4 carries the time sensitive information about in navigation message. So information in subframe 4 actually helps receiver to relate two different time standards one another. So one of them is GPS time and the other one is coordinated universal time, which is also known as UTC. So when it comes to GPS time, it is the standard time of GPS system, which is also symbolized as GPST, stands for GPS system time. So UTC is the standard for the world. It means the rate of two standards are virtually the same. Specifically, the rate of GPS time is kept within like 1 microsecond and usually less than 25 nanoseconds. Of the rate of UTC is determined by uh, USN or master clock. Is some additional knowledge if I just if you prefer internet you can see these things. Exact difference between these two constants is navigation message that give the time difference and rate of system against UTC. So that's something you need to keep that on in your mind. So the rate of UTC itself determined very carefully. It is of course there are about 65 more than 50 time laboratories and more than 100 atomic clocks all over the world and which are in remarkable stability, uh, and also it is more stable than the rotation of earth itself, so such that UTC and the rotation gradually get out of sync with one another. Therefore, in order to keep discrepancy between UTC and Earth's actual motion under 0.9 seconds, correction of 1 second, it is called a leap second. Uh, Discrepancy between UTC and Earth's actual motion, which is 0.9 for of 1 second is called a leap second. Uh, so, in other words, the rate of UTC is consistent and stable all the time. But the numbers which deals with the movement of time changes whenever 1 second leap 1 second leap second is introduced. So hope you understand about UTC. Then leaps, when talk about more about GPS time, leap seconds are not used in GPS time. Leap seconds are not used in GPS time. So GPS time is a continuous time scale. So nevertheless, there are movement. So when we talking about subframe 4 navigation message includes this relationship between GPS time and UTC. It also subframe 1 contains some information about GPS. We can also coefficients that used to estimate the difference between satellite clock and GPS time. So that's about the another requirement, GPS time. And the other one is details on the satellite clock status. So when it comes to satellite clocks, uh, it's a when it comes to satellite clocks, it's a main thing which we have to focus in design of the GPS satellites, which have been changed year by year. But each generation satellites have similar characteristics. Uh, one is satellite clocks. So um, early satellites were known as Block 1 satellites. Then next one is Block 2. Then comes Block 2A. Even amid of changes in satellite design, one of the common elements from very beginning of the system is the GPS satellite has carried its own onboard clock. So these clocks are known as time or frequency standards. They are in form of very stable, accurate atomic clocks that are now regulated by the vibration frequencies of at, at two elements, atoms of two elements, cesium and another one is rubidium. So there are three rubidium clocks on first three GPS satellites. At this time, cesium clocks were performing bit better than rubidium. So subsequent satellite had four clocks, three rubidium and one cesium. As I previously mentioned, these early satellites were known as Block 1, so Block 2 and Block 2A. These satellites carry four clocks as well, but there are two rubidium and two cesium clocks. These are some from additional knowledge for you. So on the subsequent blocks like 2R, 2RM and 2F satellites, there are three improved rubidium atomic frequency standard clocks. So this is referred as RAFS clocks, rubidium atomic frequency standard clocks. So they are also regulated by rubidium. So these improved clocks have proven excellent performances. So there has been some considerations of equipping upcoming Block 2F satellites with hydrogen maser clocks, so which have been even higher precision than rubidium clocks. And when it comes to the operation of clocks in any satellite is completely independent from another clock of another any other satellite. So tracking stations of control segment monitor all the satellite clocks. So control segment monitor all the satellite clocks, and also control segment could continuously adjust. Then all the satellite clocks stay can stay in lockstep with the GPS time standard, which I explained earlier. But that is not what is done. Constantly tweaking the satellite onboard clock would tend reduce their useful life. That's the one issue we have to face. So instead, each clock is allowed to drift up 1 millisecond from GPS time, and their individual drifts are recorded and uploaded into subframe 1 of each satellite navigation message. Uh, so that's something you need to understand. So there are I have explained 4 requirements of a GPS signal: uh, code, and also location of the satellite, and also time and satellite clock status. So let's move forward. We have to focus about the characteristics of GPS signal. As you see, here's the simple wave equation for GPS signal. Here U is the oscillation variable, and A is the peak amplitude of the wave, and T is of course time, and K and B are arbitrary constants which are representing time and displacement of offsets respectively. Then when it comes to wavelength of GPS signal, so uh, GPS signal generators, sometimes called clocks as well, cause frequency of modulated carrier is measured in hertz. So it can indicate elapsed time between the beginning and end of wavelength. So this is very uh, bit in useful bit of information in finding the distance covered by a wavelength. So wavelength is approximately if we say wavelength is lambda, it is approximately equal to c divided by f. So here lambda referred to length of complete wavelength in meters, of course. So c is equal to speed of light. Here what you need to remember is keep that in mind. It's very important. Speed of light which is corrected for atmospheric effect. So not just speed of light, it need to be corrected for atmospheric effect. So f is frequency in hertz. So for example, if an GPS generator transmits a modulated carrier with wave with a frequency of suppose 10 megahertz, and the speed of light is approximately 3 and 8 zeros behind it. um, then lambda can be found as c divided by f, so 30 meters. So it means modulated wavelength would be 30 meters long, approximately 100 feet. So that's about wavelength. And when it comes to frequency, it is measured in hertz, and wavelength which with duration of 1 second is known as 1 cycle per second. It has a frequency of 1 hertz. That's International System of Units definition for hertz, so otherwise SI definition for hertz. So frequency of 1 hertz is this low. So lower sound, as you know, that we can hear, we can detect, is 25 hertz, and maximum one is I guess 20 hertz, 20 mega kilohertz, something closer to that. So most of the modulated carriers that which use in GPS have frequencies that are measured in units of million cycles per second, or megahertz. So three fundamental frequencies assigned to GPS carriers come from part of the electromagnetic spectrum, which is known as L band. So here L band includes high frequencies from approximately 390 to 1550 megahertz with wavelengths from 15 to 30 centimeters. So the two legacy GPS carriers are L1 and L2, which has 1575.42 megahertz and 1227.6 megahertz of frequencies respectively. So, and also there's a third relatively new carrier being broadcast by some of the GPS satellites. It's known as L5. Frequency is 976.45 megahertz. So that's about frequency. So here you can see when f is 0.5 t, periodic time is 2 seconds. So f means number of flashes per second. So t and f are reciprocals. So f equals 1 over t, or t equals 1 over. So these are the basic characteristics of a GPS signal's wavelength and frequency. You have to, it's some important characteristics of GPS signals. So I mentioned about AM and FM frequency modulators and amplitude modulators based on such characteristics. So that's something additional to keep that in mind. We will explain those things in further next few videos. So today in this video we talk about what are the characteristics of GPS signals and what are the requirements for a GPS signal. So those are code, of course. Code helps us to identify each satellite, and also data or location of the satellite, or some information which we can which we can have the location of satellite by using those information. That's another requirement. And third one is information regarding amount of time signal left from the satellite, and also clock details of the satellite. So those are the signal requirements. So here we talk about what is GPS, brief introduction actually, and also we focus mainly about requirements for GPS signal, and also wavelength and frequency of a GPS signal. So let's see, hope you learn something from this video. So subscribe our channel if you haven't subscribed it yet, and turn on the notification button, and stay in alert with our channel, because we frequently update our channel with new videos. Of course, remote sensing video series is going on the other hand. So hope to continue both video series on the GPS and remote sensing. So comment section is open for you for your comments to improve our video series, and have a nice day, and see you in next video. Thank you.